How many stereoisomers are possible for this molecule? Well, first we need to remember our formula, 2 to the n equals number of stereoisomers possible, where n is the number of chiral centers. So this question is really about, can you identify the chiral centers of this molecule? So let's remind ourselves, what is a chiral center? A chiral center is a carbon that is attached to 4 different groups. So for example, here we have a hydrogen, a chlorine, a bromine, and a methyl. Those are all different. That's a chiral carbon. If any of those groups are the same, then it's not chiral, or we call it achiral. So in this example, we've replaced that methyl group with a hydrogen. Now we have 2 of the same group, not a chiral carbon. Okay, but this molecule is a ring, so let's take a look at what rings do to our chirality. Our rings are going to take up 2 of our connection points, and the question is, are those connection points the same? Or really, is the ring symmetrical? And the way we can check, if we don't see it immediately, we can take a walk clockwise along the ring, and then we can take a walk counterclockwise along the ring, and if they're the same, then it's achiral like we have in this case. If, however, we have a point of difference, we have an asymmetrical ring, and we take that walk clockwise, and then we take that walk counterclockwise, in this case we see a methyl group earlier than we would on the clockwise. So we have a point of difference, which means that we have a chiral molecule now. So we see that the molecule we've been given, this ring is asymmetric on all 6 carbons. There's no way we can slice this in which we're going to get any symmetry. So the ring is going to be 2 different connections on each of these carbons. That means all we really need to identify is, are the remaining 2 attachments the same or not? And so that means right off the bat, 2 methyl groups and 2 methyl groups, those carbons are not going to be chiral. Same thing with our double bond to the O. This doesn't even have 4 connections. Anytime you have a double bond on a carbon, never going to be chiral. That leaves us with our remaining 3 carbons. And if we remember that connected to all of those carbons is an unwritten hydrogen, that means since our ring is asymmetric and we have 2 different connections to that carbon from outside the ring, each of these is a chiral center, and we have 3 chiral centers. That means if we go back to our equation, 2 to the n number of chiral centers is 2 to the 3 is 8 possible stereoisomers. The answer is D. If this was helpful to you, be sure to follow for more tips and tricks.